the name of this unit, after our trigonometry unit, the name of the unit that we're currently on, chapter 7, we call trigonometric identities. And we've been introduced to this a little bit. But here's the definition of what a trig identity is. It is an equation that involves trig things, sine, cos, tan, secant, cosecant, cotangent. That's always true, wherever the angle is defined. So we've learned some of these already. Like two of our big ideas are identities. This was one of our big ideas from chapter 6. That sine squared theta plus cos squared theta is always 1. Another big idea from chapter 6 is that tan theta is always sine theta divided by cos theta. And since this is true, no matter what angle you pick, these are called identities. Can you see this one? That would be an identity. What did they do? Do you see they just took the big idea and rearranged it? If you multiplied both sides by cos, you would rearrange that big idea and you would get this. That's another identity. And so mathematicians found if you manipulate things, you can make a whole bunch of different things identities. And that's what this is going to look at. So, on the bottom of page, or in the middle of bottom of page 606, you have the reciprocal identities. We also know these from chapter 6. In fact, we just called them definitions at that time. We just defined cosecant of theta to be 1 over sine theta, secant of theta to be 1 over cos theta, and cotangent of theta to be 1 over tan theta. Which means that we could rearrange these a little bit. I'd like you to write these down. You could also write sine theta as 1 over cosecant theta, cos theta as 1 over secant theta, and tangent theta as 1 over cotangent theta. And because tangent is sine over cos, that also means cotangent is cos over sine. I'm going to hand out to you a whole page of identities that we're going to prove. So the big thing in this next part of this unit is something called proofs, and I'm going to introduce you to it. And we're going to develop strategies for solving this. You're going to get a lot of questions in this unit that say prove. And we'll start with number 5. Number 5 says prove cos of t secant of t equals 1. And I'm going to, if you don't have loose leaf, I have extra here. We're going to do this on a separate piece of loose leaf. Does anyone need paper? Anybody need paper? all these extras. Everybody else, everybody good? I have extra up here. You can come take as much as you want. At the end of class, you can steal it. I won't do that. Now, what does a proof say? It says, I want you to show me that cos of t times secant of t is equal to 1. Is this always true? Okay. So first of all, in a proof, very important, what we're going to do is at the equal sign, draw a line that separates the left side of your equation from your right side of the equation. Because in a proof, you don't know they're equal yet. That's what you've been asked to show. But if you say they're equal before you've shown it, it's an automatic 1 mark deduction. So the easiest way to avoid that 1 mark deduction is to draw a wall. And nobody can cross over this wall. And it separates your left side and your right side. And now it becomes a puzzle. How can we get the two sides to look exactly the same? And the only thing we can use now are these tools, and I guess we also have the big idea. Sine squared theta, okay? You're going to find out from your formula sheet there are some other tools we're going to be allowed to use later, but for right now, these are the only things you're allowed. And with the things that you're allowed, it means that if you want to, and you have a sine theta, you can always change it to 1 over cosecant theta. If you want to and you have a cosecant theta, you can always change it to a 1 over sine theta. You can change anything you want, but your goal is to make the left side and the right side the same. So when I look at this, I might decide to change everything. I might decide to change only one thing. Okay? And this is part of what makes the identities proofs hard, is because you don't know what you need to change, and we'll develop some strategies along the way. Strategy number 1 is that if you look through them all, every single one can either be a sine or a cosine. Check it out. Cosecant, you could change it to sine. Secant, you could change to cos. Cotangent, you could change to cos over sine. And tangent, you could change to sine over cos. So all 6 trig functions can be reduced to 2 trig functions if you wanted to. This is going to be a big strategy. In fact, I'll use it in this first one. So in this first one, I'm like, I have cos, but can I change secant to something? Yes. Secant is 1 over cos. And then we have a fraction times a fraction. Can you see that if you had a cos t on the top and a cos t on the bottom, those would simplify? And then you would just have 1 times 1, which is 1. As soon as your left side and right side are the same, we write a little statement that the left side equals the right side. The 3 dots in math mean therefore. Therefore, the left side equals the right side. And and this is like a fancy math thing that often happens after proofs. The Latin abbreviation QED. How's everybody's Latin? No? No. QED, the end of a proof. Apparently it comes from, my pronunciation is probably going to be terrible, but you won't know. So you just pretend, right? Quod erat demonstratum. That what has been asked for has been demonstrated. You asked me to prove this. Look, I got the left side and the right side the same. I'm done. So it's basically a statement saying I'm done. This part here. Okay, let's do another one a little bit more involved. Let's go to number 8. So when you're doing a proof, the first thing you're going to do is you're going to rewrite the equation. So number 8, I have sine x secant x. And I have the equal sign because this is what I want to prove. Prove. And then we draw our line. If you put equal signs on the line, you lose a mark. They're not equal. Two sides you don't know are equal yet. That's what we want to prove. And we're going to use the strategy that you can change everything to sine or to cos. Which means I'm not going to change the sine, because it's already sine. But I can change the secant, and the secant would change to 1 over cos. And this is over 1, so if I multiply the tops and multiply the bottoms to get a single fraction, and that is going to be, that's the reason we started with our fraction work at the beginning, because the main strategy will be, can you write something as a single fraction? So on the left side, I wrote it as a single fraction, but my left side and my right side aren't the same yet. And here you have a little bit of options, okay? You could, right, what can we change tan to? Big idea. Tan is sine over cos. So you could change this side to sine over cos, and then they're exactly the same, so we can write our statement left side is equal to right side. The little square box is like my own thing. I like to have a little symbol at the end to say that I'm done. I had a university math textbook that had a little square box at the end of proofs, and then I just kept it as my own thing. You can add a smiley face. You don't have to add anything. It's just my own little touch. So this part here just says, I'm done. I've solved it. Both sides are identical. Okay? Is there another way you could have done this? Yeah, you could just change this side. You could change to tan x. And then you wouldn't have to write anything on that side. That would be fine as well. Okay? The exam actually draws the line for you. They got so mad at taking off marks for students who made it equal too soon. They actually drew the line on the exam so that hopefully they don't have to take off marks. They break it up with the left side and the right side already. Okay, we'll do. So you will be able to do up to, I think up to 24. You'll be able to do up to 24. We're going to do 2 more together. We're going to do 14 and we're going to do 15. So 14 has sine u cosecant u plus cos u over secant u. So again, you write it out first, equal to 1. Draw the line at the equal sign. This is what we want to prove. And our fraction work is going to come into play. I've taught you one main strategy so far. You can change everything to sine or cosine. Then after that is just fraction work. So, in this question, I would have sine u over, and I would change the cosecant u to 1 over sine u. Plus, I have cos u, that I would keep the same. But the secant u, I would change to 1 over cos u. And now we have fractions divided by fractions, because technically this fraction on the top is over 1, right? You have one fraction on the top, one fraction on the bottom. If you have a fraction divided by a fraction, keep the top the same, multiply by the reciprocal. Keep the top the same, multiply by the reciprocal. And then how do you multiply fractions? multiply your numerators, multiply your denominators. So sine u times sine u is sine squared u. And cos u times cos u would just be squared as well, cos squared. So we change things to sine and cosine, then we use our fraction work to simplify it as much as we can. And I get sine squared u plus cos squared u. I'm very close. What do I want it to equal? 1. You see what I can do? This, right? This is an identity, which in an identity means whatever you have the left side, you can replace it with the right side immediately. It's one of the ones on your formula sheet. All of these ones are allowed, so anytime I see a cotangent, I can change it to cos theta over sine theta. If I have sine squared plus cos squared equals 1, I can change it. If I have this, I can change it to 1 because it's an identity. And then my two sides now are both 1, so I can write my statement, my left side equals my right side, Q, E, D. Woohoo! So I sort of liken identities to like little puzzles. You know they're equal to each other. Your job is to do the puzzle to make the two sides equal to each other. And you're allowed to work on both sides. Yeah. It used to be that they were like, no, you're only allowed to work on the left side. So do you know what students would do? Sometimes they'd work on the left side and get stuck. Then they'd work on the right side and they'd get them the same. And then they would just slowly erase the right side and undo it on the left side until it matched up, which was kind of pointless. So they're like, okay, now you can work on both sides. You can manipulate the left side, you can manipulate the right side. If you can make them the same, then you can make your statement and you're done, you're proof. Okay, we're going to do one more. Number 15. Prove, and we have 1 plus sine z . 1 minus sine z. And on the other side, we have 1 over secant squared z. The left side already has sine. The right side has a secant. So I can change that. Okay, when I go to my stuff here, I could either use this in the green box, okay, because secant can get changed to 1 over cos, but I can also use this in the in the purple box, because I have secant, but the secant's in the denominator, right? So if you have a 1 over secant, you can change it right away to cos. And if I have a 1 over secant squared, it is perfectly fine if you see it to go directly to this. If 1 over secant is cos, then 1 over secant squared would be cos squared. Why? Well, I could write this like this. And then I could write this as cos. But I think most of you will like to just go from 1 over secant squared to cos squared. In fact, you can always do that with anything in the denominator. If I have a secant squared in the denominator, I can change it to a cos squared in the numerator. If I have a cos squared in the denominator, I could change it to a secant squared in the numerator. Okay, I've got cos squared on that side. On this side, I have I can multiply things out, right? Maybe you notice it's a difference of squares. So all of these things from different, like differences of squares are going to come up a ton. If you do 1 plus something, 1 minus something, that's going to be 1 minus the something squared. So I multiply that out, and I get 1 minus sine squared z. We are so close here. Okay? The big idea from chapter 6 is that sine squared theta plus cos squared theta equals 1. In identities, if you can see something with one mental math change or manipulation, okay? For example, can you see it's really easy mental math-wise to get the cos squared by itself? What would you have to do to get the cos squared by itself? You would have to subtract the sine squared to the other side, right? Can you see that? If you can see that in one step, it is allowed in identities to just say, oh, I can see in one step that cos squared theta is 1 minus sine squared theta. Then you are allowed in identities. Lots of rules in identities, but you're allowed to change this if it's one step. If it's more than one step, they will say, you didn't show any work. There was someone on the exam, they had the question, and they were like, they actually wrote, ladies and gentlemen. It is obvious that 1 plus sine squared, sine z times 1 minus sine z equals 1 over secant squared. And the only work they showed was, well, I shouldn't have, well, I can undo it. The only work that's, so there, I'm done. They just took the right side, wrote it on the left side and said, no work needs to be shown. It's obvious. I just did it in my head. No. That's like multiple mental math steps to do that. It is true. They'll never give you a proof and go, it doesn't work. If they do that, they give every single student across the province full marks on a question. If they make a mistake, it's kind of a good thing. It doesn't happen very often. So, here. But if it's only one step, there we go. Like, you have sine squared theta plus cos squared theta equals 1. In one step, I could get cos squared theta by itself. Then they're fine that you don't show that. And now the two sides are the same. And we can go left side equals right side. And we're all done.